Hello everyone. So this is the sixth week of the course, Multiphase Microfluidics. Let me share my screen. Yes, yes, I am in presentation mode now. So, so this is the sixth week six of the course Multiphase Microfluidics. Let me just see my voice is audible to you. Yes, where is that? Hello. Yes, I am audible. Hello. Yes. So, so this mm, yes, I am in presentation mode. Yes. So multi-phase microfluidics, phase microfluidics, fluidics, and so far in the course, uh, in the week six especially, you are being taught about the mass transfer in the Taylor flow regimes and how this mass transfer in the Taylor flow regimes is actually affecting or so to say controlling are being done efficiently. So this these are some videos that I will be following. The respective channel names are given over here along with the link. So this will be very helpful in understanding how the boiling is happening, and so to say how this uh, pool boiling happens and how the curve comes up for the pool boiling, and along with that, so, one experimental video for boiling inside a channel which is having its dimension 5 mm. So how different flow morphologies are coming up, we will be looking at the videos. So the purpose of this particular lecture is to ease out your assignment session, to ease you up in the assignment, solving the assignment. So we will be solving 20 to 30 short questions based on the lecture have been taught in the week six, and one by one we will be looking at different aspects of the same. So for example, the first question that I will be posing is this one. So, so what do you mean by? So the question is how you can how you can scale up the micro channel. So how you can scale the micro channel, scale up the micro channel. So basically, if there is a single micro channel, then there will be different scenario. But this question you think, then I will be telling you, because if you see, if you go for this multi channels, or I mean this for large throughput, you need multiple array of the channel stack, because the amount of the product you want, or the amount of the heat transfer or mass transfer you want is very much. So for that, you need scaling up of the channel, means the channel dimension will be same, but uh, to accommodate more of the fluid at a time, being under the transfer of heat or mass, the number of stacks is being increased within the compact, ensuring the compactness of the overall instrument. The number of channels is being still scaled up. So how they are being done? You think? Till then, I will be looking at the next problem. So you think about this, and we will be discussing about the same. So some glitches are coming up. Wait, let me fix it. I mean, it is okay. Yes. So recording is happening. Yes. So no problem. So basically, scaling up the up of the channel means scaling up of the channel means what? Scaling up of the channel means increasing the number of uh, uh, units. Okay, scaling up of the channel means expanding the number of units. So this actually means like scaling in marketing means increasing the reach and the impact of the product or services by expanding its presence from multiple channels. So similarly in the microfluidic system, if you increase the channel and then you are increasing it in layer wise also. So the different stacks will be there. So how you will be doing that? By increasing the number of the channel. So the answer to the problem is like numbering of the unit or channels. So if you let me just take different color, could be achieved by having more number of more number of units or channels. Is suppose this was the stat and to perform some experimentation where this channel y-able channel. So either you can go in using two ways. First is on the same level you increase the number of channel, or you just repeat the levels itself. Though that will be three-dimensional, but that will be scaling up of the same. So that could be done. So this was it for this particular question. And next problem is which of the following processes involve mass transfer? So the question is which of the following processes involve mass transfer? question is options are: A is the extraction, B is the leaching, A is extraction, B is leaching. Let me just see. A is extraction, B is leaching, and C is distillation. Okay. ABC. B is dry. So the answer to this is, in the mass transfer you study absorption also. So you start with the diffusion, then absorption, then distillation, then extraction, then drying, then leaching. So these all are mass transfer operations. So if you remember properly, these are all correct. Along with them, what is the correct term? If absorption is there, that would be correct. And if osmosis is there or membrane separation is there, so that is the correct one. So something about the next problem that I will be asking. Question number 3 is, which of the following is correct? Is correct for high diffusive transport rate at a given storage rate? Options are: Fourier number is very high, Fourier number is very low, Fourier number is constant. None of them, none of these. So you think about this question. Just move. Yes, yes. Think about this question. So the answer to this will be Fourier FO is very high. And why this will be correct? This is very clear from the definition of the Fourier number. If you remember, when you got the definition of the Fourier number is uh, ratio of ratio of ratio of Fourier number equals to ratio of diffusive transport rate, diffusive transport rate. Fourier number is the ratio of diffusive transport rate to storage rate. And here in the problem, it has been said that this numerator is high. Okay, so if you remember, it is the it characterizes the balance between the heat conduction and the heat storage rate within a material or body. This is the important. So you just note it. It characterizes the balance between heat conduction and heat storage within a material body. Okay. So here the Fourier number is high. No? So what is the case? A higher Fourier number signifies a more rapid heat transfer. Okay, heat transfer through the body. Through the body. So if it is high, more rate of heat transfer will be available. So conversely, a lower Fourier number corresponds to a slower rate of heat transfer within the body. So now you see the options. It is very clear that A option will be correct option. Sorry. A option will be correct answer. So now looking at the next problem. This is some subjective question. Mass transfer and reaction if done in micro scale channels brings tons of advantages over conventional channels. Explain. You please look at this and pin out 2 to 3 points that will be correct about this. Why we go for the micro or meso scale channel, uh, and what advantages we get. What advantages we get when we go into the nano domain. So, what nanotechnology brings to you. So, think about this. Meanwhile, I will be then discussing about this answer to this. Just think about this and okay. So I hope you have thought about this, and as you go towards the microfluidic site, you come with the lots of advantages. The first is that surface to volume ratio increases. So so large surface to volume ratio leading to leading to large surface area for the transport phenomena like that. Okay. This was point number one. Point number two is momentum transport increases. Third is heat transfer increases. Fourth is mass transfer increases. Fifth is fifth is what? Large interfacial area will be there. So That's why all the above three increases. Area. Avoid hotspot formation during exothermic reaction. Avoid hotspot formation during exothermic reaction because much of the heat is being transported. And the seventh is small diffuser. So these are some of the advantages that I have discussed with you. You just look at this once and think of if some more pin you can pen down. So this this microchannels brings us these set of advantages. Okay, and the next question that we will be going to discuss is on pool boiling. So what is the mechanism for the pool boiling? So explain the mechanism of pool boiling and explain the mechanism of pool boiling and explain the mechanism of pool boiling. Explain the mechanism of pool boiling and yes, so this and draw the pool curve. Draw the curve. So pool diagram also is out. So let us before going to the problem, let us see the video how the boiling happens and how things come up into the picture and then so this pool boiling one you will be looking. Yes, so let me just open.
How to get the most of Grammarly free.
It's Kayla on behalf of Grammarly to tell you
Yep.
all about.
Yes, we will be looking at this. Yes, this is where. Let me just increase the screen size. Yes, just look at this. So just created by successful life navigation. So this is the beginning. How the thing, this is the curve which is QS versus the temperature gradient that we are having. You see how boiling is happening. So from the heated surface it is happening, and the pool of the water is at the top, and then you are looking at the flow structures which are coming up. So meanwhile this will be related to the uh, curve, boiling curve. So now you are approaching the critical heat flux. So when you approach the critical heat flux, your morphology looks like this. Lots of big chunks are coming up. These chunks are not like frequently smaller one, and they are at the same time getting breaking down. But initially, most of them were not progressing with each other. Rather, they were separately moving apart. So maybe I should just introduce some water. Yes. So if you see this critical heat flux, now you read, and at the critical heat flux you see what is it. Big chunk of the continuous kind of is coming. So this will lead to the formation of just after some time there will be formation of thin such layer. So you see this is the continuously pool boiling happening, and at the critical or the just after the critical stage we will see this one coming up into the picture. Now so the pool boiling this you will be clear with how the boiling happens. The the curve how it is being drawn, we will be looking at that now, and then we will be actually discussing about the same. If you see this the another one by magic marks, and this will be very clear to you now. Just see.
We know that pool boiling is a mode of boiling where the fluid is stationary in the beginning with respect to the heating surface. To understand this boiling, let's consider an example of vessel containing some water placed on a burner.
So the you see initially the fluid is stationary, and it is in the pot which is resting over the heating surface, heated surface by the flame, you see, and the pool boiling is mode of boiling where the fluid is stationary in the beginning with respect to the heating surface. Now what will happen, you see.
As the heat gets transferred from the bottom surface of the vessel to the stationary water,
Now the heat is being transferred, and
it starts rolling up and down.
so there will be the beginning of the natural convection. Why that will happen? Because fluid at the bottom will be directly in contact
Then
with the
bubble
heated
formation
surface.
takes place. And after some time the water gets boiled. This process is a pool boiling process.
You shall look at how this natural
Pool
convection
boiling
will happen.
takes place in different stages. They are free convection boiling,
First stage is the free convection
nucleate boiling,
the nuclear boiling.
transition boiling, and film boiling.
Yes, the last.
These different stages can be easily plotted on a heat flux temperature plot.
This plot only I was talking about and told you to draw. Heat flux versus temperature.
X-axis represents the difference between the current temperature and saturation temperature of water, which is represented by delta T excess. And y-axis represents the heat transferred to the water per unit surface area of the vessel, which is represented by heat flux Q dot boiling. The curve OABCDE is known as the pool boiling curve of water. Here, curve OA represents the stage free convection boiling.
Yes. So
Curve
the free
ABC
convection boiling was
represents the
the
stage
initial one,
nucleate
where
boiling.
lower fluids got the lower density, and because
Curve
of that,
CD represents the stage transition boiling.
buoyancy came up and they went up.
And curve DE represents the stage film boiling.
These are the 4 stages.
Now let's understand each section of the curve one by one. Let's discuss about curve OA, represents the stage-free convection boiling. When we light the burner, heat transfer takes place between the vessel and water due to free or natural convection.
Then natural convection is stabilized there.
We can see that the values of heat flux and delta T excess start increasing.
You see how that increases.
And when the temperature of water reaches its saturation temperature, that is when delta T excess attains a positive value.
Yes.
Then boiling takes place. This stage of boiling is known as free convection boiling. Curve ABC represents the stage nucleate boiling. As we can see, nucleate boiling is divided into 2 parts. Curve AB represents liquid entrainment and curve BC represents critical heat flux.
So
Now
it is
first,
divided
let
into
us understand liquid entrainment.
flux.
Due to continuous heating, we see that the value of delta T excess increases and the bubbles are formed at the bottom surface of the vessel. These bubbles move upwards and carry some water along with them, but they collapse after covering some distance in the water.
So due to the continuous heating, the value of delta T excess
This is known
increases.
as liquid entrainment.
So liquid entrainment.
We see that the disturbance caused by liquid entrainment in the water increases the heat transfer coefficient, so the heat flux also increases. In curve BC, we see that as delta T excess further increases, the bubbles start forming at a faster rate. These vapor bubbles move upwards and merge to form numerous continuous columns of vapor in the liquid. The bubbles in the column then move upwards to the free surface, where they break up and release their vapor content. Due to this, the heat flux attains its maximum value, known as critical heat flux. Thus, the complete stage of boiling from A to C is known as nucleate boiling.
And this is split into 2 parts, you see.
Curve CD represents transition boiling. When the vapor of delta T excess increases beyond the critical point, we see that the heat flux starts decreasing. This is because a large fraction of the heated surface of the vessel is covered with a vapor film. This vapor film acts as an insulator as its thermal conductivity is lower than that of water.
Yes. So
Thus, the value of
that's why
heat
the
flux attains
heat flux
its minimum value.
becomes low.
Point D corresponding to the minimum value of heat flux is known as Leiden-Frost point. In curve CD, both nucleate and film boiling takes place partially. Thus, this stage is known as transition boiling. Curve DE represents the stage film boiling. We see that after the transition phase, the delta T excess further increases, due to which the vessel surface is completely covered by a continuous stable vapor film. Now, because of high temperature, we see that the radiation heat transfer takes place
Radiations comes in
between the heated
last
surface and the water
film.
through the vapor film. Thus, this stage is known as film boiling.
Okay, so these were the stages that
Draw the pool boiling curve.
we just talk about the same. And if you saw this, then you must have noticed that
And film boiling.
how different stages came up. So the starting from the coming up of the free convection boiling, then the nuclear boiling and the transition boiling, which comes just after the nuclear boiling, which is the mixture of both, and then the film boiling. So the pool boiling is a mode of boiling where the fluid is stationary in a beginning with respect to the heated surface. Okay, so then you saw the curve that was showing uh, uh, Q rate of boiling, and the unit was watt per meter square to that of the delta T, and this is the excess temperature. How we are calculating it? This is the T surface on which the boiling is happening. Suppose this pot is there, so the temperature of this Ts minus T saturation, and these are in Kelvin or degree Celsius. So you saw this curve coming up like this, and then you notice some of the points. So you divided these three regions, four regions rather. One is the mixture of both, and uh, I will be explaining you a bit more about different regions. So the first region that you had is the pre-convection boiling region, which is represented by OA. Suppose this is the O. So there you had uh, uh, heat transfer is happening between the vessel and the water due to the free or natural convection. Okay, so the heat flux and the delta T excess starts increasing, and the temperature of the water reaches its saturation temperature. Okay, when this T excess increases and attains the positive value, then boiling takes place. This stage of boiling is known as the free convection boiling. So these are negative till when? Till A. These are -5, 0, and so on and so forth. But when this attains the positive value, then this boiling starts. And once the boiling starts, the subsequent stage comes into the picture. So this stage of boiling is called the natural. So this is the convection. Another one was nucleate boiling. So here you reach the temperature Ts somewhere, and at that point this T axis will be 0. And then the next stage you had where you had the continuous heating is happening. The value of the delta T axis is now positive, of course. So it increases and the bubble are formed at the bottom of the vessel. This bubble move upward, but they collapse after covering some distance. So they collapse after covering some distance. So rising bubble carries some water along with them, as they will be anyway taking some of the water with them. So the when they collapse after covering some distance, this is called liquid entrainment. So because of that liquid entrainment, which is happening over there, because of the liquid entrainment which is happening over there, uh, there will be disturbance caused by the liquid entrainment in the water. That increases the heat transfer coefficient. So heat flux also increases. So heat transfer coefficient is being increased by water entrainment. Okay, and now the next stage, which is the later part of the nuclear boiling, is the BC. What is happening there? Further increase of the delta T axis, which is the x-axis, uh, the bubble starts forming at the faster rate. Now the rate of the bubble formation is very much like in the video we saw, uh, and uh, these vapor bubbles move upward and merge to form the numerous continuous columns. So lots of continuous columns of vapor coming up. So it seems like they are continuous column, but they are nothing but the combination of many small bubbles. Uh, the bubble in column then move upward to the free surface where they break up and release their vapor content. Okay, at the top they are releasing the vapor content. Due to this, the heat flux attains its maximum value, uh, and also you call it as a critical value. And this is the stage of the boiling. A to C we call it. So A to B and B to C then, and A to C, so which is called the nuclear boiling. Okay. So now afterwards, what you saw? Afterward, you saw that further increase in the delta T E axis had its movements side of that critical point, which is the maximum point, and now the curve is coming down. So coming down means it is decreasing heat flux. So why that is happening? Because large fraction of the heated surface of the vessel is covered by what? Vapor film. So this vapor film acts as an insulator, and the thermal conductivity of this vapor film is low than the water. Thus, the value of the heat transfer attains its minimum value, and now this minimum value is the point D correspond to the minimum value of the heat flux, which is known as Leiden first point. So I had one question based on Leiden first point. So I will be keeping up the up here. So the question is, which of the following point is question number 6 is which point in whole boiling curve is first point. Options are, so you mention the above curve only. A is A, B is B, C is C, and D is D. D is D. Okay, so as we discussed, the answer to this will be D corresponds to minimum value of uh, heat flux. So corresponds to the minimum value of heat flux. This corresponds to the minimum value of heat flux, and now the another question, that is, which stage of food boiling involves radiation influence. So the both of the lecture, the second and the third lecture of the week was completely the in-depth discussion about the heat transfer and the mass transfer along with the boiling in the channels. So that's why this question is more like confined into the boiling domain. Okay, so this boiling involves radiation influence. So options are A is O to A, B is A to C is B to C. Okay, then You see, T is C to D, and E is E is what? E is what? D to E. And if you just think about this, you just think about this, and then let me know. So like I said, here we were at the Linde first point, and the Linde first point, if you reach afterwards, afterward you will be going into the film modeling section, and that is nothing but the last increasing stream of the boiling curve, where that happens after the transition phase, where the t axis delta t axis increases further, uh, and then the completely the vessel surface is completely covered with the vapor film. So because of that high temperature of the vapor film, the radiation heat transfer takes place between the heated surface and the water through the vapor film, and water is resting over the vapor film. Thus, this stage is known as the film boiling. So which stage this effect of radiation is coming up? It is coming up in DE, which is this one. This is what? This is film boiling. This is critical point. And the first point, this is critical point. In this domain, entrainment happens. Okay. So that was it for this particular lecture, and especially for the boiling. Now we will be going towards another question, that is again based on what has been taught in the week lecture, and the question is about dimensionless number. Uh, Question is about dimensionless number, and that is explain dimensionless number analogous to Nusselt number in heat transfer. So you just think about this. The number analogous to Nusselt number in heat transfer. Maybe about the Nusselt number we have discussed in the last class also. So I have discussed Nusselt number in detail in the last class. Maybe that question is over here only. So let me just read that. So I will be actually telling you Nusselt number in the the corresponding number in the mass transfer thoroughly to you, so that will be anyway clear to you. So I will be taking complete discussion of this Nusselt number on the same slide so that things become very clear to you. Yes. So I have connected this last lecture with the today's lecture. So in order to explain that, we will be using this one also. Yes. Okay. So you see, Nusselt number is ready, and we will be going to explain another number soon. So just think about this. What is that number? You just think about this. The number is what? The number is Serwood number. So Serwood number is analogous to Nusselt number in the heat transfer, and Serwood number is a number which will be used to explain the same phenomena happening in the mass transfer. So think about this. What is the definition of that? If you remember, the Serwood number is first came into the explanation when you was actually in the mass transfer discussion, and that is defined as the thermal conductivity comes into the picture if you are in what, in heat transfer. There the mass transfer Serwood number comes into picture, and that Serwood number, if you see, that Serwood number is analogous to what you are being explained in the heat transfer. So the definition of the Serwood number says is a dimensional number used in the mass transfer. It represents the ratio of the total. So I will be just explaining you it here. So this is what Serwood number is. Serwood number, and this is ratio of total mass transferred, total mass transfer, and this transfer is happening because of what? Convection plus diffusion. Okay, so convection plus diffusion and divided by rate of the diffusive mass transport. Rate of the diffusive mass transport. Upper one was also rate. So apart from this, if you just see this, this is convective mass transfer to the mass diffusion rate. To the mass diffusion rate, and this is this is Km divided by d by L, which is KML by d. This is diffusibility. Sorry, and this Km is mass transfer coefficient. Okay, so what is the take home message here? If you see, what is the take home message? If Sarud number increases, if Sarud number increases, then what will be happening? Sarud number increases, then what will be happening? Uh, Convective mass transfer will be increasing. Mass transfer will be increasing. Means characteristic length will be increasing. That generally doesn't happen most of the time. Length will be increasing or mass diffusibility will be decreasing. It will be decreasing. Okay. And this is analogous to Nusselt number in the heat transfer. Okay. So this Sarud number we discussed in detail, and now the Nusselt number is what? Nusselt number is resistance due to the conduction in the fluid. Okay, to convection in the fluid. Okay, that is L by K divided by 1 by HA. That comes out to be H by K, K fluid, thermal conductivity of the fluid, or HL by K fluid. So accordingly, we discuss that if Nusselt number is greater than 1, means resistance to the conduction is higher, means Q convection is higher than Q conduction, and generally Nusselt number is greater than 1 for many fluids. It means Q convection is always higher than the Q conduction most of the time. Now, if Nusselt number, which is the stationary resistance to the moving resistance, in other way we see, and that is HL C by K. If Nusselt number is more, means moving resistance is more than the result is more heat transfer. Okay, moving fluid result in more heat transfer because stationary resistance is higher, or vice versa in the another case. Similarly, similar to the Nusselt number, there is the Boyd number is the heat transfer. So that definition is there. So that's it for the this question. Okay. So now we will be moving towards the another problem, which is Hatta number. So explain Hatta number. Explain Hatta number. Question is, I think this is 10th question, 11th question, I think, because Nusselt number, Bat number, Schmidt number, those were three questions along with that. So this 11th question is explain Hatta number in detail. With its example applications. So if you see this Hatta number in one of the lectures that has explained about this involve the reactive systems. So basically, the subject that you study in the chemical reaction engineering, you study the two subjects that you study, the mass transfer and the chemical reaction engineering. These two subjects actually differentiates you from rest of the other engineering departments, and this two subjects involves basically rigorous formulations and conceptual clarification about the mass transfer modes and mass transfer and the uh, and this we see chemical reaction engineering. This Hatta number is the the clear explanation I expect from you. And just think about this. You just think about this, and this will be very great if you actually answer this question. And this was explained in the class in terms of the diffusion length, diffusion time scales, obviously. But the thing is, further in-depth explanation of the same, if you can point out. Okay. So this Harta number sometimes you call it Harta modulus or Harta number comes up there, and this Harta number is what maximum possible conversion in the film compared to with maximum transport through the film. So in this way you can define it. This could be defined in another way, like in the class it has been defined, but the another approach could be, if you see maximum possible conversion in the film compared to with maximum transport through the film. Okay, so this is it, and this also equals to this always so equals to characteristic length, diffusion time to characteristic diffusion time to reaction time. Characteristic reaction time. If we go further into this, this is maximum possible conversion in the film. So in terms of rate of the reaction or reaction engineering, we are explaining it to maximum diffusional transport through the film. Diffusional transport through the film. Through the film. Okay, so this in terms of concentration it comes out to be so like uh, in the film if the conversion is happening then KCAI to CB at 0, that actually happens based on the if the first order reaction second order reaction is assumed to that by this is the fixed lab we are writing, so this comes out to be KCBDAI, this is diffuse rate divided by KAI. Okay, so what it tells, what Hutton number tells, whether the reaction is fast or slow, we focus on unit surface of the gas liquid interface. So gas liquid interface is there. We assume that the gas phase resistance is negligible and we define a film conversion parameter which is the Hutton number. And if this Hutton number is greater than 1, so most of the reaction occurs in the film and the surface area is controlled rate factor. On the other hand, different things will be happening. So if MH is greater than 1, all reaction occurs in film, surface area is controlling rate. Surface area is controlling rate. Okay, and in another one, if MH is less than 1, no reaction occurs in the film. In film, bulk volume becomes the controlling rate factor. Controlling rate factor. Okay. So means when Hutton number is large, we should pick a contacting device which develops or creates large surface area. Means energy for the agitation is usually an important consideration in these contacting schemes. So that has to be taken into account. And if the MH is very small, this Hutton number is small, all we need is large volume of the liquid. Agitation to create large interface area is of no benefit here. So you got it. So yeah, this is also there like spray or the plate columns should be efficient device for system with the fast reaction means large MH, while the bubble conductors should be more efficient for the slow reactions with small Hutton number. Okay, so we discuss about the Hutton number now, and I hope the discussion is fruitful to you. And let's move towards the next problem, which is on the next number, uh, that is number. Explain the number which is analogous to Prandtl number in the heat transfer. Explain the number. Explain the number. Dimensionless number. Number analogous to Prandtl number in heat transfer. So I will be discussing about the same. You just think about this. Okay. So if you remember, you will be getting this out. So think about this, and soon we will be looking at the same. Uh, and this Prandtl number is what? In the heat transfer, you see Prandtl numbers comes into picture, and this number is usually used when there is storage along with the diffuser. Okay, so the Prandtl number is what? If you see, the Prandtl number is the Prandtl number is just change the color. Yes, the Prandtl number is number is equals to momentum diffusivity to the thermal diffusivity. Okay, momentum diffusivity to the thermal diffusivity, and this is again equals to the kinematic viscosity to the thermal diffusivity. If you see in the form of expressions, you will be having Prandtl number equals to Cp mu divided by K equals to alpha. This is hydrodynamic bond. This is for hydrodynamic bond layer, and this is the thermal bond layer. So this is the one point, that is Prandtl number is in heat transfer is analogous to estimate number in mass transfer. And what is the estimate number? The estimate number is the estimate number is let's change the color so that things become segregated. Estimate number is mu by d. There you are mu by alpha, here mu by d. Diffuse because of mass transfer comes into the picture. Viscous diffusion rate to that of molecular mass diffusion rate. That is mass diffusion rate. Okay. That is, it is used to characterize fluid flow in which there are simultaneously momentum and the mass process. You know, it is used. It is used to characterize fluid flow in which these there are simultaneous momentum and mass transfer, diffusion convection process. Okay. So that's it for this particular question. Okay. Okay. Which of the following is correct? Now the next question is question. Which of the following is correct regarding Sherwood number? Okay. That is A, B, C, D. So you need to pick up the four from the four options. Which of the following is correct? So I will be putting down the options. These options are in the form of this in the form of this expressions. So 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 that will be again clear to you why uh, that comes into picture. But the thing is, uh, okay, this comes into the picture now. Let me just go to the 316 I have to teach. Yes, chalo. Yes. Okay, the expressions for serial number I am going to, and let me just write down the expression. Yes, yes, yes. Yes. So this is serial number is the function of Reynolds number. Serial number is the function of Reynolds number, Scaven number, and geometric parameters. Serial number is the function of Reynolds number only. Serial number is the function of Reynolds number and Reynolds number. Which of the following is correct? You just think about this. And this is for the microfluidic system. Okay, so that has to be written in the question. This is for microfluidic system, micro channel, and gas liquid flow. Okay, so If you remember, the answers to this will be, there will be multiple answers. This is correct. Why this option is correct, we will be looking at. This is function of Reynolds number, obviously, but this is not correct. This is Reynolds number is correct. Why this one is correct? So there is something called this GZ, Grudge number. So this Grudge number GZ is equals to, this Grudge number is equals to what? This Grudge number, this is related. This is related only for the heat flow in the through the tube in a circular pipe, and this Grudge number is equals to the one which is defined in the lecture, which is L divided by D times Reynolds number and ischemic number. And you know this ischemic number is what? This is mu by D. Just we discuss this ischemic number, which is mu by D. So now you know this ABC is the correct answer for the given question. And now I want you to look at the question about about the optical, about the optical measurement technique. So what's optical measurement technique? The measurement of the concentration inside the microfluidic channel. What is true for measurement of concentration inside microfluidic channel system through optical techniques. So the options are so option A is monitor color change using pH indicator. pH indicator. Okay. Option B is bubble size change. Yes. So I hope I am audible. Yes, I am audible. And just see this bubble size change. And the third is C option is liquid induced fluorescence. Induced fluorescence. What is none? So what are the correct options? If you remember the second lecture of the week, there it has been told about first lecture, I mean, there it has been told about the various methodology for measuring the concentration in the microfluidic channel in order to quantitatively understand the mass transfer phenomena which is happening over there, and how much mass is being transported through uh, slurs to the bubble, or slurs to the bubble to the wall, or from one particular flow morphological structure, be it bubble or sludge, to the wall, or vice versa. So, the answer to this is A, B, C. All these are factors that could be used to get insight over that and explain. Now I will be looking at some of the more involved problem, that is like uh, let us see the next question that we are going to solve is it will be anyway related to your the lecture today. Okay, so let's see this and sorry. Okay, so what could be the possible ways of mass transfer? Okay, so I am talking about like the modes of mass transfer and how this mass transfer will be happening. So discuss about, question is discuss about complex mass transfer mechanism, mass transfer mechanism in Taylor flow. Okay, discuss about complex mass transfer mechanism in Taylor flow. Okay, so you just discuss some of the points about that, like from where to where the mass transfer is happening and how this is happening, and if there is some integrate flow structure which is helping in the overall mass transfer direction control, then that. So you think about this, and then we will be looking for that. Okay. So till you think about this, and then at the same time you saw this how the this overall phenomena are happening, and also there is one another very good video success. Uh, Maybe this one or this one. Let me see. This one is what? This or this one. You see, this is happening in the channel. So, I will be actually looking for this. So let me see if it is there. So what you have to do is just look at this, and this is happening in the channel which is 5 mm in dimension, and beautiful phenomena is happening. So that will anyway help you in order to grab the overall understanding that you got about the mass transfer and heat transfer in the microfluidic channel or micro channels or mini channels, so to say. Uh, Especially the Taylor bubble which is happening. So that if you see, you will be able to relate it to the content that you have been taught till. Okay, and obviously I will be going to take that on the screen so that you see this. This is by separation and heat transfer, and very good and well explained phenomena experimental setup which is happening in the 5 mm in a diameter channel. You see boiling how happening in the channel. You look at it. Till I am explaining, you look at it. So you see the increase in the number of the bubbles are replicating, and then you will see the continuous bubble formation is happening, and continuous bubble coalescing is happening, leading to the continuous film and Taylor bubbles are coming up into the picture. So why the nuclear boiling is there, and why uh, the, the 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 convective regime is coming into the play and coming into the picture, we will be looking at that. As you see now, most of the water is changed into the vapor, and still the continuous phenomena is happening. Continuously, you are boiling the thing. So, but if you looked at the phenomena that was there, uh, you must have appreciated it, and then how this this actually happened inside the microfluidic channel. All the flow morphologies that you have been taught of or discussed about. So if we go for the next problem, that is this one, the complex mass transfer mechanism in the Taylor flow regime that we were discussing, is there could be these things happening. So let me take the pen and if you see, these things could be happening here. First is there could be two systems. First is the reaction system with systems. First is what? There will be two systems. Suppose this is what with reaction on the channel wall. On the channel wall. Okay. And there could be another one without reaction on the channel wall. On the channel wall. Okay. Okay. So if you see this in the reaction on the channel wall, if you go deeper, you will be looking at this in another way, that is gas to solid mass transfer. So this is your this is your channel, this is your one of the bubble which is there. There is a thin film, this is the tail, head and the body of the bubble, and if you see, there could be gas to solid mass transfer. This gas to solid mass transfer, if you see some, let me see what happened. Oh, so let me just see this. Yes. And let me just present it up. Yes. No problem. Okay. So mass transfer. So this, see, uh, there are two paths. Path one is via liquid slug. There, what you had via liquid slug, if you go, what you had gas liquid mass transfer at the interface via front and the rear bubble cap. Gas to liquid mass transfer and the interface via front and rear bubble caps. Okay, and then transfer of dissolved gas molecule from sludge to the wall. Okay, this is the two phenomena that could happen if that is happening via the slug. Okay, and if you want me to extend it up further, is if the reaction is happening on the channel wall, then there could be another path, that is path 2. This was path 1, another one is path 2, is via liquid film. That was the via liquid slug, here via liquid film. So via liquid film, what could happen? Gas bubble to liquid film. Okay, first from this region, gas bubble to liquid film, and then liquid film to the catalyst wall. Suppose that the wall of the channel is made up of catalyst. Liquid film to catalyst. Okay. So this path 2 is the dominant mechanism, especially for long walls. If the long bubbles are there, so long bubbles are there, then there could be this possibility, and in some cases, the liquid film may become saturated, eliminating this route completely. So, so that case also be there. If the liquid film becomes saturated, and there will be no further this so there could be this possibility, and now if you see this, if you see this if you see this uh, liquid film to the catalyst wall is happening, then another path was that we have talked about this, uh, if for the system with the reaction on the channel wall, if the liquid is the continuous phase. Okay, but the initial discussion that we had there, the first point that we had is the the system with the reaction on the wall that was there obviously, but this okay. So for the for solid mass transfer, gas to solid mass transfer, you have considered, and if you consider another one, that is liquid continuous phase, then liquid solid mass transfer could also happen, and there will be these things. So if for liquid continuous, that will be sludge anyway phase, what could happen, there could be liquid solid mass transfer, directly liquid to the catalyst solid, it is happening. This will be followed by the del this k by delta h equals to k by delta is time. So that is so this if you remember that here what will be happening, two zones, there will be recirculation zones and the film surrounding. So what is there, if this is the gas, this is the gas, here the sludges, there will be recirculation zones. Okay, and film surrounding it, so films will be surrounding it. Okay. So this is the film. So here mass transfer from the circulating vortex to the film will be happening, and then transport through the film. So what will be happening? Mass transfer from circulating vortex to the film and transport through the film. Okay, so this could be happening there. And for the system without reaction on the channel wall, there could be two things. For, let me change the color. For gas is the continuous phase. Here, what will be happening? If the gas is the continuous phase, you see, from here mass can be transferred. So there will be mass transfer by cap and fill, mass transfer via cap and fill. This can happen. No solid wall transfer. No solid. Okay, and then if you actually see this phenomena to happen, then uh, you will get the various uh, interfacial uh, expressions accordingly if for different phenomena to happen. So question is right interfacial area. So the two, so for the in general the mass transfer for the Taylor flow, if you write no, so there you have to calculate the expressions for AGL, ALS, AGS, ALS, and AGL. What are these interfacial areas? Expression for in Taylor flow. Okay, if you remember this, so in the Taylor flow, how these things came up into the picture, let me just do it quickly for you. So there you had total gas, solid mass transfer. If it is happening with without reaction transfer, this is equals to mass transfer via just see some problem is happening. Let me see this. No, it's mass transfer via fill. Okay, plus mass transfer via gap. Okay, and if you write this, two parallel steps are happening. So this will be KGLS, AGLS equals to AGS, AGS plus 1 upon, these are the resistances that you are right, KGL, AGL for the gas to liquid, and KLS, liquid to solids, GLS. Okay, and if you see this, this is happening over here. It's the bubble, gas to liquid. Here, if it is in contact, gas to solid, and then liquid to solid. Okay, so you see this, and when you rewrite the expressions for that, if you take this to be D, this to be delta F, this to be this is what LB, this is for the sludge if you consider, and this is what LS. So if you see this and if you derive, then you will be getting AGL to be 4 B minus delta F2 is equal to E to the volume you have calculated LB plus LS B square. Okay, ELS similarly you calculated, that came out to be 4 LS plus D minus 2 delta F divided by LB plus LST, and another one was AGS is 4 LS, no, 4 LB minus D minus 2 delta F divided by L plus B LLB plus LS. So that's all for this particular question. Okay, So I hope this you got. And now you got to know about the overall phenomena of the mass transfer, how it is happening into this, and about the Hata number also. The thing that you have been told in the class, I will be just repeating that again. The Hata number we had clearly, but the one that has been told in the class is HA square, which is equals to tau d divided by tau y, which is reaction time. Tau d is the diffusion time to, this is what, this is reaction time. Okay, so that's all for today, and thank you so much for your attention. Thank you so much. Thank you. Let me just exit it. Stop present. Okay.